Hey, so here's how you do these. You have this function, and your first step is to do the partial derivative of f for x and set it equal to 0, and do the same for f of y, set it equal to 0. So if you do the partial derivative of this with respect to x, you get 3x squared minus 3 plus 3y squared, setting it equal to 0. You have that. And then just do this one before you start solving anything. So if you do the partial derivative with respect to y, you get 6xy. Setting it equal to 0, you get 0. So now you have these two equations, and you're trying to find the critical points. And the critical points have to satisfy both equations. And so you're going to solve for x and y to get the points. This one comes up a lot, and it's super easy. Because x would be 0 and y is 0. But that doesn't mean a critical point is 0, 0, because again, the critical point has to satisfy both equations. And if you put 0 for x and 0 for y here, you would get 3 times 0, blah, 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 that's 0, minus 3 plus 3 times 0, blah, 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 is 0. So you'd have minus 3 equals 0, and that's not true. So 0, 0 is not a critical point. But you do have that 0 is a critical point, or is going to be a part of one of the critical points for x equals 0, and y equals 0 as well. So then test x equals 0 and y equals 0 into this equation, since you got it from this equation, fy. So testing x equals 0, if you plug x 0 into this, you get 3 times 0 squared, that's 0, minus 3 plus 3y squared. So that gives you minus 3 plus 3y squared, gives you 3y squared equals 3, which gives you y equals plus or minus 1. So now you know that you have critical points at x equals 0, and then plus 1 or minus 1. So 0, 1, and 0, minus 1. Then you do the same by testing y equals 0, because remember, again, we didn't have the critical point at 0, 0, but we had x being 0 is going to be a critical point, and y being 0 is going to be a critical point. So then you test y equals 0. When you plug that into this equation, you get 3x squared minus 3 plus 0 equals 0. So 3x squared equals 3, which gives you x equals plus or minus 1. So now you had y was 0 and x was plus or minus 1, so you also have these critical points, 1 comma 0 and minus 1 comma 0. So now you have your critical points, and now you have done that just through the first partial derivatives to get to the critical points. That was all step 1. Step 2 is doing the second partial derivatives. So you just do what you had here, 3x squared minus 3 plus 3y squared. You take the second partial derivative with respect to x, so you just look with respect to x here. So that would be 6x. 3x squared is the only one, so you get 6x fyy. So if you take this one with respect to y, well, the y goes to 1, so you have 6x again, and then fx with respect to y. So now you go back to this one and do it with respect to y. So these are constants that go away, and you get 6y, and so you have fxy is 6y. The discriminant formula is d equals fxx times fyy minus fxy squared. And so then when you plug them in, you get the 6x times 6x minus 6y, all of that squared, which gives you 36x squared minus 36y squared. So that is your d equals formula. In other problems, you might just get a number, which is great, because when you're testing, you're seeing, well, is d greater than 0? If it is, then, well, it's going to either be a maximum or minimum. If it's less than 0, then you're going to have a saddle point. But unfortunately, we can't figure that out right away. And so we have to evaluate the critical points. So that's step 4. So step 1 was first partials, getting the critical points. Step 2, second partials. Step 3 is getting the discriminant. Step 4, now evaluating the critical points we had here. You have to test every one. So I separate them into bullets, and I'll test just in order. So at the critical point 0, 1, you plug it into your discriminant now. So discriminant at 0, 1. So x being 0, y being 1, it's just going to be pretty simple because you're going to have 0 minus 36. So it's minus 36. That's a negative, so it's less than 0. As I said before, less than 0, D is a saddle point. Now you need to know, where that happens. It happens at 0, 1, but you need to know at what value it is. So now you have to plug the 0, 1 back into the function, the original function, because it happens at 0, 1. So what value is coming out at 0, 1? Plug it 0, 1 into here. So 0 cubed is 0 minus 3 times 0 is 0 plus 3 times 0 times 1 squared. All that's 0. So you're just getting 0. And that can fast forward the next one. So you end up getting 0. So your saddle point of 0 at 0, 1. Doing the next one, it's identical just because you're going to end up having the 0 and minus 1, but minus 1 squared is still 1, so it's going to be minus 36 is D, which is less than 0, meaning saddle point. Plugging it back in, it's going to end up doing the same thing because this 0 in this equation for x, since x appears in each one, is going to zero out the whole equation. So again, it's saddle point of 0 at 0 minus 1. This kind of makes sense because the way saddle points work. Now you test the last two. So you have 1, 0, the point 1, 0. Plug it back into the discriminant formula. So d of 1, 0, plugging it back into the d equals 36x squared minus 36y squared. So you have 36 times 1 squared, giving you 36 minus, and then there would be y squared and y 0, so that's 0. So 36 minus 0 is 36. Since it's greater than 0, we now know d is greater than 0, and that means that it can either be a minimum or maximum. It is a minimum when fxx, so this one, when that one is greater than 0, it's a minimum. So if d greater than 0 and fxx greater than 0, you're getting a minimum. D greater than 0 and fxx less than 0, you're getting a maximum. The only way I remember that because it's kind of counterintuitive, being the fxx greater than 0, greater feels like it would be max, but it's minimum. So I just try and remember the counterintuitive. It's always going to be like the opposites. Anyway, so we had fxx was 6x. So how is that greater or less than 0? Well, remember that we're testing the point 1, 0, and x is 1. So 6x, so 6 times 1, that's 6. 6 is greater than 0. And since it's greater than 0, and I said if d is greater than 0 and the fxx point is greater than 0, it's a minimum. So that's great. We learn it's minimum, but now we have to find out where it occurs. So we go back to here, at what value. So we plug 1, 0 back into the function. This one's not going to zero out because of having a 0 in it, because the y only appears here. And so these ones are going to end up giving us a value. So going into it, we do at what value. So it was x cubed, so that's going to be 1 cubed minus 3x, so 3 times 1, plus that gets zeroed out because of the y being 0. So you get 1 minus 3 equals minus 2. So we have a local minimum of minus 2 at 1, 0. And then it's almost identical here. So you have minus 1, 0. The d is going to be the same things because x squared, even if it's minus 1, becomes positive. So you have 36. So d is greater 36, which is greater than 0. So it's going to be a minimum or a maximum. Then we go back to the fxx, and it's 6x. Well, the x here we're testing is minus 1. So 6 times minus 1 gives us minus 6. Minus 6 is less than 0. So we have a d greater than 0 and fxx less than 0. So it's a maximum point. So now we find out where what value the maximum point is. So at what value? F of minus 1 is 0. We plug minus 1 back into our original equation. We get minus 1 cubed is minus 1. Minus 3 times minus 1, well, that's adding the 3. So minus 1 plus 3 gives us 2. So we have a local maximum at 2 at minus 1, 0. So you have the saddle points, and you have a local min, and you have a local max, and that's how to solve it.